Joining swimming already, alright? Still need to. No one will join swimming. Only the DSAs will continue to swim. Okay, then what's the point of having open house? Oh, sure. What a waste of my time. Okay, let's do this. What was the last thing I did for circular motion? Last thing. The car going around a circle, and I finished that already. Did I come up with the equations for that one already? Yeah, I came up with equations for that one already. Fs equals Fc. Did I do the mu n equals to Fc also? I did that, so the whole equation is done already. Okay, good. All right, now we're gonna do a little bit more, like a bit more advanced one, a bit more wonky one, okay. All right, this is called bank turn, car on a bank turn. Okay, so we're gonna do a car on a bank turn, car on bank turn. Anyone watch Cars? Lightning McQueen, the Daytona, right? You watch that, right? Okay, so a bank turn is basically, you see, now it makes sense, right? When I use this kind of references. When I was teaching this, like before Cars came out, nobody knew what the heck I was talking about. Yeah, it was, right. But some people don't watch it, see, so they don't know. But you all know, right? So it's like at a certain age, like you watch it as kids. But if it came out for like the teenagers, they won't watch it, see. It's a kiddie show, right? So they won't watch it. So now you know what I'm talking about. I'm talking about a car on a bank turn. We're talking about bank turn, so the road looks like this, right? The road looks like this, okay? Right? The road looks like this. I try to draw it as accurately as I can, okay? So this is the, how the right? So the car is approaching you, right? As it turns, now it's approaching you. So can you try to figure a way to draw this? Yeah, draw this. I'm gonna draw the car as well. I'm gonna draw the car. So Lightning McQueen should be red, right? Okay. There we go. Right. So this is the car on the bank turn like this. Right. So you're looking at the front of the car, right? Looking at the front of the car, right? And we're gonna do this now. Firstly, what kind of circle is this? Is this horizontal circle or is it vertical circle? See, right, the car is like, it's traveling like that. Yeah. So is it a horizontal circle or is it a vertical circle? Yeah, horizontal, right? It's still a horizontal circle. The car is still going around like that. You see? Right? It's going this way out and then going back around like this, then this way out and going back around like this, right? In a bank circle. Yeah, the American racetracks are the weirdest things ever. I don't understand how it works though. Like it's not very exciting. You're just going around and around and around and around. Do they go around it 500 times? Is it why they call it Daytona 500, right? Yeah, they call it Indy 500, right? What? And then people are getting very hyped up about it. I don't understand. F1 I can understand, right? Got the twists and turns and corners, right? What? You see them go around this thing 500 times? Okay. All right. So you must recognize that this is a horizontal circle, and the most important question is this. Okay, most important question is this. Where's the center of this circle? Right? I'll tell you the answer. The center is here. Right? Above the ground, a lot of people always mistake that thinking that this center of circle is on the ground here like this, right? The center. That's not it. Right? Because the circle is at this level. The circle is at this level here like that. Right? So the center of the circle is at this level too. Okay? Right? So let me just draw it out a bit nicer. Right? So the center of the circle is here, right? At that level, not at the bottom here. Okay? This is very important. It's very important to know that the center of the car circle is high up here, not down here. Okay? Why is that? Because if you say that the center of the circle is at the bottom here, then you will be trying to draw a centripetal force that points towards the center like that. That's absolutely wrong. Right? It's not pointing towards the center, it's pointing here like this. And right, but like I say again, don't worry, right? I told you that for all circular motion, there's only two kinds of circles. Which two kinds? Horizontal and vertical circle. I haven't done vertical circle yet. I'm still doing horizontal circle. And your first job is to identify where the center of the circle is. Okay? Good. Then now we draw forces acting on the car. Okay, now we're going to draw forces acting on the car. Okay? Now, here's the thing, okay? When you're doing car on bank turn, you always have to remember that the reason why some tracks are on a bank turn like this, right, is to reduce the requirement for friction. Yeah, I know it's a bit strange, but we do not need friction here. So in a very, like, if you don't want to dwell on too much about why this happens, and you don't have to, seriously, you can just simply say, just remember this: bank turns, right? Friction at all. I'm just saying that, right? The reason why some tracks, right, some race tracks are banked, right, is to reduce the friction requirement, right? Is to reduce the friction required. Are we okay on this? Okay, so if that's the case, there's actually only two forces to draw, which is what? The weight and the normal contact force, right? And the normal contact force. It's actually only these two forces to draw. You don't have to worry about friction, because some of you might be wondering, does the friction point up or the friction points down, right? So down here I'm telling you no friction required. We don't draw the friction. There's only these two forces: normal contact force and mg. How about the driving force though? How about the driving force? Driving force, where's the driving force? Yeah, the driving force is out of the page, right? Or the air resistance is into the page. Those two forces will not contribute to your circular motion, right? It's there, but I just don't draw it. It's there, but I don't draw it, okay? Right, so we got your normal contact force here, we got your weight here like this. Oh, some more, I think I have some questions from Glendon's side as well. Hang on, let me just, because he's not able to make it today, but he did drop me some questions. I will have to try to go through those questions, but let me just do a quick check what he was asking for. Okay, he was asking something about dynamics, and he was asking something about a vertical circle, so we'll deal with that later. Right, I'm not done vertical circle yet. Okay, right. Here's the next most important thing. Pay very close attention, okay? All right. What are you supposed to do here now? Resolve which one? No, you're not supposed to resolve mg. Okay? So this is, again, this is a very, very unique exception. Okay? When you see there is circular motion around a bank turn, right? You do what you can to find the resultant that points towards the center of the circle. You do whatever you can to point towards the center of the circle. What happens if you resolve weight by accident? I'm going to draw this. What happens if you resolve weight? Right? Don't draw this. What happens if you do this? What happens if you resolve weight? It means you resolve the mg cosine theta and mg sine theta. What will happen? Right? It doesn't point to the center, right? You're just making it very complicated. Okay? Because, then you need to go and find some of the horizontal component of this thing. You're making it very complicated. So when it's a bank turn, you resolve the normal force to the vertical and the horizontal, because that horizontal component, this horizontal component, is going to be pointing towards the center of the circle. Are we okay? All right, but then how do you resolve this N force then? You have to do some trigo, right? You have to do some trigo. Okay. All right. So this one here, there's no shortcut. I want you to work it out. There's no like sine is slope and C is contact force. I want you to work out the angle. Right? Think of math, think of trigo, think of geometry. Right? Think of where the angle is and then give me the components, these two orange components here. Which one? You ready to give an answer? Okay. Vertical one is n sine theta. Vertical is n cosine theta. Then this one's n sine theta. Okay? Alright. Let me help you out here. Right, for those who can't see this. Is this theta? Alternate angle is theta, right? Then this one will be 90 minus theta. Okay? If that's 90 minus theta, that means the top one here is also theta. Ian, you okay there? Can you see this? Can Right, so theta here, 90 minus theta, and then theta up there. Okay, good. Right, let's clean up the image a bit, but there you go. Right. So what's the conclusion regarding the forces? equation. Give me a sum. N cosine theta equals to mg. Does it have to? Why does it have to? What happens if it's not the same? Yeah, if it's not the same, right, then the car will either slide up or slide down, no? Right, the whole idea is that this is a horizontal circle, means that it maintains at this level, right? It maintains at this level, right? So in order for it to maintain at this level, the n cosine theta must be equal to mg. So write that down. You can write down n cosine theta equals to mg. Okay, you can write that down here, right? N cosine theta equals mg. And then the next thing you can write down is n sine theta equals to fc. So now we know what provides for the centripetal force. N sine theta provides for the centripetal force, right? N sine theta equals to either mv square over r, right, or mr omega square. But usually for racetracks, they will go with mv square over r. Okay, right. Now they don't usually do this next thing I'm gonna do for you. They don't usually do this in school, but I'm gonna do it for you. Right. I'm gonna ask you to consider this. Can you all imagine, guys, what happens if the car slows down? Let's say the car decreases its speed. What will happen to this car? Right, it will start to slide downwards, right, if it slows down. What happens if it starts to speed up? Let's say it wants to go even faster. Then it will start to rev outwards, right, like this. Right now, if it starts going faster, it will slide upwards. If it starts going slower, it makes sense, right? It's kind of like the velodrome, right? A velodrome. I don't know whether you all watch the cycling ones, right? When they cycle faster and faster and faster, the guys tend to slide all the way to the edge of the track, right? You know that that's a very steep slope. It's actually not easy for anyone who's standing, right, and try to climb up there. It's a very, very inclined slope. So if they want to get up there, right, all the way up there, they have to go really fast, right? Then they'll start to spin, then they start to cycle, and start to speed up, and they go towards the outside like this. Okay? So I want you to understand this, right? If the car does go faster, if the car does go faster and faster and faster, there will be friction now, right? Where would the friction point then? So as the car speeds up, as the car starts to move towards the edge of the track, where would the friction point? The friction will point downwards, right? Okay, the friction will point downwards. And the whole idea is, right, the pointing down part, there will be a component of that pointing down part that gives you this additional centripetal force. Right? If your friction is pointing downwards like this, so I just draw this here, right? I wanted to show you that there is a horizontal component that gives you additional centripetal force. And that makes sense. Because if you want to go faster around a circle, you must have more centripetal force, you must have more friction, right? You must have more centripetal force. So the friction will contribute, the additional friction will contribute to the additional centripetal force. Okay? But what did I say just now? I said that most of the questions do not need you to calculate the friction. You understand that? Right? It doesn't need you to calculate the friction. So usually they omit the friction altogether. But if you had to, if they tell you that there's friction and they tell you the friction is pointing down like this, right? Pointing down like this as the car is like trying to accelerate, right? Okay? As the car is trying to get faster, then you would need additional centripetal force. This is like to add on the amount that you can get, right? To add on the amount that you can get so that it can travel faster around the track. But like I said again, don't need right? 9 times out of 10, 9 times out of 10, all right? But for the A-level side, they have to consider the friction. It's quite annoying, right? So the mathematics is a lot more complex. This is quite complex for you already. All right, this is considered quite complex for you already, okay? All right, can I move on to the next thing? All right, I'm gonna move on to the one more thing. I'm still on horizontal circles, I believe. I'm still on horizontal circles. What have I done so far? I've done the pendulum. I've done the, okay, how about this one here? You all watch MotoGP? You know what MotoGP is? What is it? Yeah, MotoGP, right? The motorbike race, right? MotoGP. You know, when they're doing a turn, right? When they're doing the turn, what do? they lean, right? So it's like, if let's say this is the bike here like that, and then okay, you don't have to draw this because this is really hard to draw. The guy leans, right, like this. You know, oh my goodness, how do you draw this thing? Okay lah, like that lah. Right, he leans this way, right? Okay, right. Then which where is he turning then? He's turning to the right side, right? I mean, if he's going into the page, he's going away, right? If he's going into the page, he's trying to make a right turn. He's trying to do a right turn like that. Okay, can? All right. Let's try to understand by drawing the forces acting on him. So where's the center of the circle? So this time around, it's a flat track, right? So we're back to a little bit basic stuff. It's a flat track, but because it's a motorcycle, he needs to lean, right, as he's trying to make a right turn. So he's trying to lean to the left side, trying to lean to the right side in order to make a right turn, right? Okay, so this is right turn. So where's the center of the circle? Huh? Where's the center of his circular motion? Yeah, here, right? Somewhere around here. Somewhere around here, right? The center of his circular motion, somewhere around here like this. Hey, cannot. Can center of circular motion somewhere around there, right? Okay. What are the forces acting on this dude then? There's a mg. There's a contact force. And then, so you have to consider that there must be friction, right? Okay, like I say again, you have to infer that there's friction. Okay, so we infer that the friction is here. Okay, but the point is, I want to show you that sometimes some textbooks, right, they combine these two arrows. They combine these two arrows. They will combine these two arrows into a force that looks like this. They call it the contact force. So instead of seeing these two arrows, right, you see this thing here called the contact force like that. You understand this? Okay, so you've drawn the diagram already. Try to use pencil to draw the forces. Okay. Yeah. Yeah. Right. And understand that the contact force is basically the sum of normal and friction. Sum of normal and contact friction. Sum of normal and friction combined. Whoa, wait. What's going on, dude? Hey, Ian, where do you go?
I think my Wi-Fi crashed.
Okay, are you back?
Yeah.
We good? Can? Right, I just want to show you as many scenarios as possible, that's all. Okay, I'm just showing you all the scenarios so that you don't get too confused. Cannot. Done? I have this guy at a HDB flat, HDB car park, right? This guy is like driving one of the damn high-end Ducatis. Like, I mean, since we're talking about motorbikes, right? This dude, like, he parked his Ducati like right there, and you look at it like, whoa, this thing there, I think that costs at least like the price of a car, man. Yeah, like HDB car park. I suspect my that particular HDB car park, right? I think got a lot of rich people though. Let me tell you why. Okay, it's very strange. Okay, so there are three cars randomly, three cars. Right, the car plate number is 1883. What are the chances, right, of three cars in the HDB car park with having the same number? You know what I mean? And it's like, I always try to look out for the people who are getting in the cars, see whether they change cars or not. You know, they like decide to go here, and then hey, shit, wrong car. Then after they walk to the next car. Very strange car park because yeah, the yeah, they don't have like one single expensive car. No, I feel that there are some families with like two or three cars in yeah HDB flat. What's going on, man? Okay, can I close this now? Ian, you done copying? Can I do the next scenario. Okay, next scenario is this. Still horizontal circle. This time round, the Chinese wedding dinner table. Random, right? That thing they call a lazy Susan, you know? You know what a lazy Susan is? Oh no, you don't bake cakes. Lazy Susan? Lazy Susan, yeah, yeah. Go and take your home econs lah. Go and take home econs. Then you learn how to like deal with things in the house. Okay, so the lazy Susan or the turntable, if you want, right, in the house. Sorry, at the Chinese wedding dinner table, right? I don't know. Maybe some of the houses might even have this in your dining table. That thing that glass plate that turns in the middle, right? Okay, can so you have this turntable is gonna when it's gonna make a turn, right? It's gonna make a turn, right? We're gonna place some objects on it, right? And then like you all when you're all kids, right? You all go and right, you all go and start spinning the thing, right? You're all guilty looks all coming out already. You put an object in the middle, so I'm gonna put an object in the middle like this first, right? This is probably like the salt shaker or the soy sauce bottle. Put in the middle, okay? I put one slightly further away, right? And I put one at the edge, right? I put one at the edge. So we got three objects here like this. Right? You understand this? Right? Circular motion, huh? Okay. Number one, the one in the middle, does it have circular motion? Don't have. The one in the middle is just rotating. Right? He's just doing this. Right? He's not going around a circle, he's just rotating. So that's not circular motion. Oh, lucky I put the cap on. Okay? Then the next one will be this one has circular motion. This one will also have circular motion, right? Now the question is this, what's giving them their centripetal force? They need to have centripetal force, right? If you spin them in a circle and they do go around a circle like that, you have to conclude that they have centripetal force. They must have centripetal force. The question is, what's giving them this centripetal force? It has to be friction. If you cannot figure out what force is it, so you conclude that it's friction. Okay? So you see this object here, and you see the other object there, right? Okay, let's draw the friction forces acting on them. Where are the friction forces? Huh? Pointing inwards, pointing towards the center, right? So do you understand? Can we conclude that for the one on the outside, it needs a higher centripetal force? How do you know? How do you know that it will be a higher centripetal force? Okay, right. So what we can do is this: we can use a formula. We can look at the equation to prove that it will be higher. Okay, let's look at the equations. What are the equations? Fc equals to mv square over r. Okay, let's try to analyze this first. Mv square over r. Okay, both of them have the same mass, right? Same mass, this mass m. Okay, right. Now we know that the one outside, will it be traveling faster? Will it have a faster v? Oh, it will have. Yeah. Uniform group last time? Huh? Never uniform group. Oh, DSA don't need uniform group. No wonder you don't understand this. Uniform group? Never. Uniform group? Anyone? Girl grades, brigades? No. Okay. All right. Then this is lost on you all of you. Ian, uniform group in secondary school? Hello, hello. You're muted.
I skip everything.
You skip everything, not even the marching. Yeah,
Oh, I just say I got sick.
Walao eh. No one has experience in marching here at all. My goodness. Okay. Anyway, so you see the people who are in parade as they march, right? Okay. Let's say they have to make a turn. I don't know whether you notice this, but the dude on the outside here have to walk really, really fast. He has to walk really fast to catch up because the guy in the middle he just needs to do a small turn only. Right? So based on this, I'm just trying to tell you that the object on the outside will have a greater speed. It will have a greater speed because it's like as the thing turns, the other way you can do is this. The other way you can understand is this. What is V stand for again? Uh, not quite. For circular motion, there's a special name to this V. No, not at all. Angular velocity completely wrong. No. You know this. You flip to the front again. What was that name I gave the velocity for the objects? There was a special name to it. Linear velocity, otherwise known as tangential velocity, otherwise known as circumferential velocity, right? Okay. Notice the object on the outside has to travel a big circumference in the same amount of time to make a round. So you have to tell me that you have to agree that V is bigger for the one on the outside. Cannot. Right? You want to write this down somewhere? Yeah, write it down, write it down. Nothing on the phone is that important at this point in time. Not important one. Right? The V is bigger, right? Okay, good. But here's the problem, guys. mv square over r. Is r bigger for the outside object? R is also bigger for the object on like near the edge, right? So how do you reconcile, v squared divided by r? Is it going to be bigger for the object on the outside? Is the centripetal force going to be bigger? This number is big, the bottom number also big. So it's hard to judge, right? I know it's squared, right? But exactly what's the effect of it, you don't really know, right? So the best thing to do here is to compare using another centripetal force equation. What's the other centripetal force equation? Fc equals to what's the other one? M r omega squared. Good. M r omega squared. All right. Now this one is easier to understand. Okay. Question: what is omega? Darlene, whatever you said just now. Angular velocity, right? Omega is angular velocity. What does angular velocity mean? What do you understand about angular velocity? Time taken to, I mean the speed of covering the angle, right? Angular velocity is how much how many angles you cover per unit time, right? How much angles you cover per unit time. Correct or not? Okay, guys, inner object and outer object. Inner object, outer object. Do they have the same angular velocity? Think about this. Do they have the same angular velocity? Do they cover the same angle per unit time? Right? When you rotate the table, if this is the line, you rotate it later, it will cover here, it will cover here, it will cover here, right? Right or not? So then when it goes back again, right, they would have covered 360 degrees in the same amount of time. Omega is the same for them, right? Omega is the same for them. So if omega is the same for them, then it's a lot more easier to compare. Because mr omega squared, omega is the same for both objects, right? Right? The one on the outside, R2, the one with the bigger radius, will have a bigger centripetal force. Understand this? Right? So let's say I call this object A and object B, not 1 and 2. Right? So object B requires, right? Notice how I phrase this. Object B requires a larger FC. Right? Notice how I phrase this. I say it requires. I don't say that object B has, right? I don't say that object B is given. It's not given. It requires. It requires a larger centripetal force, right? And the answer is what? Why is it? Why does it require a larger centripetal force? Because it's further away from the center. You understand this? Okay. But what provides for this centripetal force again? One more time. Right. So friction, right? And specifically, what kind of friction? Static friction, right? So static friction, Fs, right? Static friction provides for the Fc. Okay, so you need to do a bit of throwback to topic 2. What do you understand about static friction? Like static friction, what do you understand about the properties of static friction? Static friction is what? The friction that what? Static friction, what does static friction do? Okay, so static friction prevents the object from moving. Right or not? Prevents the object from moving. But for any surface, right, is there a maximum static friction that you can exert? Is there a maximum? So any surface, right, any surface, every surface right? Every surface has a max Fs, right? Any surface has a maximum static friction. Okay? Depending on what? What's depending on what? Fs equals to what? What's the equation for static friction? Fs equals to mu S n, right? Okay, static friction or coefficient, coefficient of static friction, sorry. Right? Okay. If let's say it's a very smooth surface, let's say it's a very smooth surface, what's mu S? Mu S will be very low, right? Very small amount. If it's a very rough surface, then mu S will be higher lah. Understand? So if it's a rough surface, rough surfaces can give more static friction. Smooth surfaces will give less static friction. Right? You understand this? Okay, good. Because now I'm going to ask you this. Let's say you do the thing you do at all those Chinese wedding dinners. What do you do? Spin this thing, right? And then see the things fly off, right? And then you all laugh, right? Let's say you do that thing, right? You spin, 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 spin. Question: which object will fly off first? Right? In this one, B will fly off first, right? So that means that if you spin this table faster and faster, as the table spins faster, okay, as the table spins faster, the first object to fly off is B. B will fly off first. Then the question is why? Why does B fly off first? Okay, and the answer is based on whatever all the statements I've said before. Okay, B will fly off first because object B requires a larger FC at any time. Anytime at any speed, right? B will always require a larger centripetal force than A. Right? If the surface cannot provide more static friction, then B will fly off first, because if you don't have enough static friction, then B will not get enough centripetal force, then B will fly off first. Okay, I'll write this down for you. But I just want you to take note of the thing first. Right, I'll screenshot this for you as well. Okay. Right, I'll give you the reasoning. B will fly off first because B at higher speeds, at higher speeds, right? The turntable is unable to provide the static friction required for B's centripetal force at the higher speed. Okay? Yeah, you should first start off with B requires a higher FC than A. Okay? So you should start off by saying B requires a higher centripetal force than A. Then at higher speeds, the turntable is unable to provide the centripetal force, the static friction required for B's centripetal force at the higher speed. Right? It's just not enough static friction. That's what I'm trying to say. Okay? So you got to understand the logic. The logic is this: if you want B to go around faster, B will need more centripetal force. Of the two, B already requires more centripetal force than A. So at a certain high enough speed, right, the static friction is not enough, right? The maximum static friction that the surface can provide is not enough for B's required FC. Okay? So one more time, the rule is this: you want to go faster around, you must have more centripetal force. Then your question will be, can you provide? Can you provide? Is there enough of this force to provide for the centripetal force required? If you can't provide, object will fly off. Okay? So therefore, I want you to write this equation down. Mu Sn, which is the maximum static friction, equals to m RB omega max squared. Right? I want you to write this equation down. Mu Sn equals to m times RB, radius of B for object B, to provide object B from falling off, to prevent object B from falling off, times omega max squared, the maximum angular velocity that you can go before any object falls. Okay, brain fry already not? Oh yeah lah, still okay, right? Right. But I'm going through as many scenarios as I can, right? So that when you start doing the questions, it will be very smooth for you, right? And chances are the scenarios that I go through are exactly the questions themselves, right? This will not be the case for a lot of other chapters, huh? Right? Other chapters, okay lah, for some of the chapters, not a lot. For this particular chapter, chapter 10, right? Chapter 10 is a nightmare. I hate teaching chapter 10 every year. Chapter 10 is this thing called gravitational field and electric fields at work, right? I hate that chapter because that chapter, right? The teachers always come up with weird contraptions and weird designs. Then the question is very difficult after that, right? But for circular motion, still not so bad, right? Still can, I still can go through all the scenarios that you may encounter. Okay, last scenario for horizontal circle. Can I clear this now? Last one. I'm going to clear this one. We're going to do the last one. Okay, right? The last one will be this. Right. Last one is this. I want you to remember that the plane, an aeroplane that flies, right? Okay, an aeroplane that flies. I know this is not a very nice looking plane, but this plane is banked, right? And it's trying to make a turn. So this plane is also making a turn like that, right? So that it's making a turn like this, right? And just the most straightforward things. Where's the center of the circle? Right over here, right? The center of the circle is over here, right? Because it has to be at this level here, this same level as the plane, right? Center of circle is over there. It's a horizontal circle, so it's not a vertical circle. It's not one of those like fighter jets is doing loop the loop. That one we haven't deal with yet because that one is vertical circle, right? So we're gonna do that later, right? Once I finish this, we take a break. We can do the vertical circle already. And vertical circle is a nightmare, so I will have to go through that slowly, right? Not really slowly. I have to go through a lot of scenarios. But the important thing is this, right? Because your teachers don't teach you this, planes fly because there's this thing called lift. This is different from helicopters. Helicopters have propellers, right? Helicopters have propellers. Helicopters uses thrust, right? The propeller push the air down, right? There's the thrust force up that balances or maybe bigger than the weight, causing the helicopter to accelerate upwards, for example. You understand this? Right? But a plane does things differently, yeah? Right. Now I do want to go through the plane mechanics for a while. So I'm really gonna talk about the plane. Right. So when you look at the plane from the side view, okay, you all notice that it sort of looks like this. The plane sort of looks like this, right? Where's the plane's engines? Where's the plane's engines? No. This I'm talking about your commercial, like SIA plane. Where are the plane engines? Under the wings. Under the wings, right? The Airbus has two, right? Per wing, right? Huge Rolls Royce engines. Yeah, they're Rolls Royce. Yeah, RR engines. Okay, right? They're under the wing. Okay, right? What do they do? What do the engines do? I mean, from the side view, it kind of looks like this, right? It's just a cylinder, right? Isn't it? What do the engines do? Basically, they just suck air, right? They suck air in and they blow air out, right? That's what the engines do. Okay, and because of that, it makes the plane move forward, right? The plane will move forward because of the engine. You see, right? The engine is not a vector engine. The engine can't turn like that and then fire upwards like this, right? Only some fighter jets can do that. the engines on your plane are fixed like this, horizontal. So when this engine starts working, the plane will move forwards. But how does the plane go up? How does it lift up? There's no propellers. These engines cannot turn. It's not a vector engine. So how do the planes go up? Right? Right. So I'm going to go through this with you. I'm going to tell you how the plane flies upwards, because I think that this is something that all students should know. Right? Not students. Every human should know. You all take planes, right? You all don't know how it flies, right? Okay. So you have to look at the wing. Right. So I'm going to zoom in on the wing. Okay. Ian, are you okay there? And I'm going to zoom in on the wing. So the wing when I zoom in looks like this. No, not quite. Something like that. Okay. So when you cut the cross section of the wing looks like this, right? This is a bit exaggerated, right? But this is what happens. So as the plane moves forwards, right? As the plane moves forwards, air will move above and below the wing, right? Air will flow above and below the wing. You understand this? Notice how the curvature at the bottom here, right? The air starts to slow down here. It actually slows down here because it kind of like wells around here like this, so it kind of flows this way. But the top part is completely aerodynamic. The top part, right? The air rushes on top and it just right. So the speed of the air on top is very high, and the speed of air at the bottom is very slow at the bottom here like this, right? This is fast. Okay, the speed of the air is very fast on top and very slow at the bottom. Okay, this creates a low pressure on top and a high pressure on top. The difference in speed creates a difference in pressure. High pressure on the bottom, low pressure on the top, like this, right? Why? Because the air moves very fast on top, right? So there's very little air on top, but the air moves very slow at the bottom, so there's like an accumulation of air at the bottom, so there's a difference in pressure. Are we okay in this? Right? It is this difference in pressure on the top wing, on top of the wing, and at the bottom of the wing that creates this effect called lift. And this is the force that results in the plane flying up. This is how planes fly, right? The lift will literally lift the plane upwards like this, right? High pressure bottom, low pressure top. Okay? And so you must understand one thing. So when a plane flies, right? When a plane flies, where's the lift force pointing at all times? The lift force is always pointing above, right? Perpendicular to the wings. Perpendicular to the wings. So if let's say I bank like that, right? The lift force will change where? It will change angle, right? But it will be perpendicular to the wings. You understand this? Can Alright, good. So understanding that lift is perpendicular to the wings, right? Perpendicular to the wings. Now we look back at this diagram here. So where's the lift force for this plane? See, you're now looking at the back cross section of the plane like this. So you can see the wing going like this. So where's the lift force for the plane? There you go. Right? So now you understand that the lift force is perpendicular to the plane of the wings. To the wings of the plane. The plane of the wings. Sorry. It's just a very lame joke. Sorry, it's an aeroplane, so not a plane. Okay. Then the weight of the plane is here. Okay? Right? Then I ask you something like this. Okay, find the centripetal force for me. Right? There's no friction, it's flying. Right? There's air resistance, but the air resistance is facing either in or out of the plate. Right? It's literally the lift versus the weight. And then you have to resolve the lift to get the two components. Right? If let's say this is theta, then this is L cosine theta, and this L sine theta. And then you know which force gives you the centripetal force, right? Right? You will know which force gives you the centripetal force after this. Can? Yeah? Okay, excellent. Ready? Okay, I think I'm gonna move on to vertical circles now, right? Finally, after all that, right? Vertical circles. Okay? Right? After vertical circles, then we will be talking about planetary orbits, but that one later lah, right? That one later, right? Don't worry, because that one I need to teach gravitation first. It's part of the same chapter. Circular motion and basic gravitation is part of the same chapter. So, yeah, there's gonna be a lot of nonsense gravitation stuff at the end. But whatever I've gone through so far will give you the foundations to be able to solve any circular motion questions. Okay, anybody wants to go use the toilet, take a snack, anything? No? Take a snack, yeah. See this one, ask people to open. Don't open on me. I must open already, then people will take on. You know, don't paiseh one. Nah, I'll take one myself. Hey, one. Nah, you can try this. You can try this one as well. You can try this one as well. Ian, go toilet ah. No, no need. No need to take a break.
I went already just now.
Oh, yeah? You went when I was teaching?
No, like
Oh,
before.
before. Okay, okay. Hang on, I just chill out for a while first. If you're not taking a break, I'm taking a quick 3-minute break. Oh, Can I? Alright. I'm gonna do vertical circles now. Thanks for letting me have a snack. I'm gonna go through a few scenarios without going through them in detail first. Number one, I want to do this. I want to do a pendulum that's going around a circle like that. Okay, vertical circle. So this is not the same as the horizontal circle. This time around, I'm going to swing the pendulum as it goes around like that. Okay, so we draw a summary of pictures first. We're going to draw a summary of pictures. So all these pictures that I'm drawing on the board, you can just draw them roughly also. Just draw them as small little icons if you want. Okay. Another one is this, and this is gonna be a bit difficult to understand. The other version is a rigid stick with a weight at the end, a rigid stick, which is gonna be different from a string. Okay, this is a rigid stick, right? And I'll tell you this, okay, Estelle, sorry, your school is very particular about this. This one here, they love to give questions on this. I don't know why. For the last few batches, right? Every time I see the paper, right? Every time the paper, school likes to do this one. I also don't know why also, right? And that's just particular to SOTA only. I don't know why also. It doesn't really happen for the other schools, but I'm still gonna teach it anyway because it did come out in the IB before. Maybe that's why they're so particular about it, because it did come out in IB before. So what is this? This is string. What is this? Rigid rod. Okay, rigid rod. Right, both vertical motions, vertical circular motions, right? Vertical circles. There's also your Hot Wheels cars. Hot Wheels cars, right? The loop, right? So you got the loop, you got a car that's going into a loop, right? Your Lightning McQueen again, right? Going into a loop like that. Okay. Any other vertical circles? If anything to do with like Singapore Flyer, London Eye, Paris View, it's all this, right? It's all the rigid rod versions. This one here is pendulum. Anything to do with like a bucket of water. Did they try swinging a bucket of water in class? Did they try showing it to you? Swinging a bucket of, oh, they didn't? Oh, okay. The ACSI one, the teacher tried before. Water splash on his head. Anything else? My brain not working suddenly. Am I missing something? Somehow I feel like I'm missing something. So bucket of water is this one also with the string, right? With the string going in circular motion. Ah, the, the question that Glendon asked, going over a bridge. Yeah, the car that's going over a bridge. Right, we consider the bridge to be a circular bridge, which is ridiculous, but we'll consider that also. So 4 different kinds of vertical circular motions. 4 different kinds of vertical circular motion. Any kind more? Any more? Don't have. I think that's about it. So for this one here, this is also like a jet fighter, right? Fighter jet that's flying in the air. If let's say you had a fighter jet that's flying in the air, you know, something like that. Okay, like this. It can go around a circle also, right? Like this. Right, it's the same idea, right? So this one here and this one here is the same idea. Yeah. So all these 4 that I've just drawn for you, they serve as the basics for all the other different versions, right? We will first start off with pendulum on a string, right? We'll first start off with pendulum on a string, okay? Right, we'll first start off with this one first. And right, so I hope you didn't draw too much detail for all these, right? But we're going to draw this one now. We're going to draw this one in detail now. Pendulum on string, okay? Right, I erase this, So pendulum on string, right? I need you to understand it kind of looks like this. Let me draw a smaller one.
Draw bigger.
Yeah, this one draw a bit bigger lah, cause I want my circle not nice. Cannot do this once a year, right? So Okay, something like that. Okay, so we have a pendulum. Ian, you okay there? Pendulum going around in a vertical circle. Okay, number one question. All right, where's the center of this circle? The center here lah. Right. Okay, what are the forces acting on this pendulum? Mg and tension. Very good, right? Mg and tension. Okay, now if this pendulum was hanging like that, guys, if the pendulum was hanging and not moving, can I get you all to agree that tension equals to mg? Can, right? Okay, now that this pendulum is going around in a circle, can you tell me what's the deal with the tension and the mg? Are they the same? Why not? You don't know. Okay, hey, I tell you this, the object is going around in a circle. Your first instinct should be saying is that it needs good. It needs centripetal force, correct? So this pendulum is going around in a circle. It needs centripetal force, which is a type of resultant force. Very good, right? Resultant force, and therefore the tension cannot be equals to the weight, because if the tension equals to weight, what happens? No resultant force, right? No resultant force, no acceleration, no centripetal, no circular motion, right? But because I tell you that it's definitely moving in circular motion, so you have to agree that the tension here is different from mg. But is it bigger or is it smaller? Think first, Okay, now you tell me why bigger. Centripetal force. Correct. Centripetal force must point towards the center of the circle, right? So by looking at this diagram here, you should understand that the tension of the string is bigger than the weight of the pendulum. Okay? Because it must have a centripetal force that's pointing towards the center. Good, right? Towards the center. Okay. Okay, can. So I need you to write down the equation for the pendulum here. What's the equation for the pendulum? T. Oh, you said resultant force, right? No. T minus mg. Yeah. Hey, make it a habit. Every time you see like forces, right, you always try to ask yourself what minus what to give you what. No, no, no. This yeah, okay, fine. He's not wrong, but that's oscillation. This is not oscillation. This is circular motion. Right? In fact, yeah, that's gonna be a big thing next time. But anyway, for now, just tension minus mg, right? Tension minus mg gives you what? Fc, yeah, centripetal force. So give me an equation for that. Mv squared over r, okay? Can? Right, tension minus mg equals mv squared over r. I must tell you this, okay? This is a pendulum on a string. The string, right, can only provide tension. The string is you know, if anything else, the string, right, is kind of like slack, you know, in any other direction. Like the tension only points up. It doesn't really, like, you know, like it's like this lah, right? It's kind of like slack like this, right? So I need you to understand this, okay? When the pendulum reaches the top, as the pendulum goes towards the top like this, and it reaches the top, the speed of the pendulum will decrease. It will actually slow down. It becomes slower. Why does it become slower? Why does the speed decrease? Why does the speed decrease? In terms of energy, anyone? Why does the speed decrease? KE converted to GPE, correct. K is converted to GPE, right? Some KE, not all. If it's all, then there's no speed, then the object will not go in a circle anymore, right? What happens when the object is trying to spin in the vertical circle and it loses all its speed, guys? Like that, right? What happens if it doesn't have enough speed, right? The circle is not complete, right? Not. So do something like this. or maybe you just go backwards also, right? The object must have enough speed in order to go one full round, right? If it doesn't have enough speed, it wouldn't move one full round. It wouldn't even go upwards at all, right? You understand this? Right? If you want it circular motion, it must have enough speed, right? Like, oh, okay, and I think I should do it this way, like this, right? Then it will complete the circle, right? If it doesn't have enough, it will just drop down like this, right? Then it wouldn't finish the circular motion. So the speed will decrease. Okay, we are assuming that there's enough speed to make the complete circle, so we just leave it as that first, right? But guess what? The speed actually will come back again, because once it goes back down, the speed will go back to its original, right? GB convert to KE, right? So assuming no other energy loss, the KE here is equals to the KE plus GP on top. Agree? Okay, but it's slower lah. It's definitely slower, right? So that's the one thing that I need you all to understand. They say uniform circular motion, right? For vertical circle, the speed is not constant. So don't go and assume that V is constant. For vertical circles, V is not constant, especially when the object slows down as it goes up. But it's still considered uniform circular motion, right? You know why is it called uniform circular motion? Because the circle is uniform, not the speed is uniform, right? The speed doesn't have to be uniform. So it is our understanding that V will change. So I need you to write down things like this. I need to write down B at the bottom, because the speeds are different. The tension is different also. No, write down the B. Write down the B. Write down the B. Okay, because I added in all the bottom parts here. So at the top, right? At the top, what are the forces acting on the pendulum at the top? Mg, which is the same Mg, and a smaller t, but then the t is pointing down. I have to draw another color. Right? I'll put a t top. Right? TT for the top side, right? The tension, and then this is the Mg. Okay or not? Okay. What's the equation for the pendulum at the top? So now it's a plus, right? Equals to mvt squared over r. Right? I hope you understand r is just the radius of the circle, right? And m is the mass of the object. One of the more popular questions for this is basically asking, where is the string most likely to break? At the top or at the bottom? Intuitively, we know that it's at the bottom. But what if they ask you, prove it? Prove that the string is most likely to break when it's at the bottom. What you do is, you make tension at the bottom the subject, and then you make tension at the top the subject. See what happens. So the tension at the top is mvt squared over r minus mg, and the tension at the bottom is mvb squared over r plus mg. Do you see that? Do you see that the tension at the top, right, is you're taking a mvt squared over r. Vt is already lesser than vb, right? The top velocity is lesser than the bottom velocity, and then you minus away the mg. So the tension of the string when it's at the top is actually lesser than compared to the tension at the bottom, where the bottom speed is higher, and you plus mg also, so the tension is bigger. So the string is more likely to break when the tension is at the strongest at the bottom. This is a very common question. They'll ask you, where is it likely to break? Then they ask you why, right? And this is a mathematical proof, right, for why it will most likely break at the bottom. Okay, so far? Can Can? Okay, good. Right. So the next thing I want to do is not the rigid rod. I will leave the rigid rod to the last part. All right, I'll leave the rigid rod to the last part. The next thing I want to do is Hot Wheels car. Right? Anybody needs to use toilet? No need, huh? Okay, I'll do the Hot Wheels car now. Right, the loop, huh? So can I close this? I'm done with this already. Right, I'm just trying to point out to you that the velocities are changing. Yeah, God. Oh, I need to. Yeah, you know what? Maybe. Yeah, I'll just take some time to. No, actually, I think I will. I'll just pass you blank paper. Yeah, I think I'll just pass you blank paper. I'll print it another day. You back. See lah, play lah, play lah, play. Huh? Yeah. You need more blank paper? No? Okay. Okay, I'm gonna do the loop now. Right? Please remind me that I have not gone through the rigid rod. I scared I forget. Right? Okay, you know what? Actually, before the loop, let's go through this one. Let's go through this one. Sorry. I'm gonna go through this one, the bridge one, because this is easier to go through first. Screw it, never mind. I just do what I need. I just do the thing I usually do. This one, can you draw the loop? Sorry. Okay, this one not bad. Okay, this is the circular loop, right? This is your toy car and a circular loop. Okay, I think this is okay. Guys, it's a toy car. Does a toy car have an engine? It has a toy engine. So number one rule is to remember this. There is no driving force. Okay, a toy car does not have driving force. So if I were to draw for you a toy car here, like this, a Lightning McQueen car here, like that, on the side, before it enters the loop, what are the forces acting on the toy car? Right? Can you draw the forces acting on this toy car? You would draw it as mg, and what else? And the N force. Okay? And is it balanced on a flat ground? It's balanced, the normal contact force must balance the mg, okay? There is no driving force, and we assume no friction also. I must also ask you to remember that this is a roller coaster as well. Roller coasters do not have engines. Okay, if you go and sit the Battlestar Galactica in USS, right, what happens is this. The roller coaster goes up. Yes, there's a conveyor belt that brings it all the way up. But right after at the top, as it falls, is just basically GP convert to KE, KE convert to GP, GP convert to KE, all the way. There is no driving force. There was only an initial amount of GP, and then everything else is just using conversion of energy, going around in loops and all that kind of thing. So it's the same thing, right? So what I'm drawing here is a toy car, or otherwise also can be known as the roller coaster. Can? Right? Now, assuming that there's no human being inside the roller coaster yet. So if you want to do a human being, right, the diagram will be similar. You'll be drawing for the human being. But let's say we're just talking about the toy car first. Now, the next thing is this. What's the difference between toy car then and roller coaster then? The toy car is not fixed to the tracks. The roller coaster has to be fixed to the tracks. For safety reasons, obviously. They're not going to give you like a freewheeling roller coaster. That's a nightmare. That's not even scary anymore. That's just like downright dangerous. Okay? Right? So the difference is the toy car can leave the track and drop off and can fall off. Okay, so we're going to do toy cars first because we want to see the toy car fall off. Okay? Alright. Now you must understand this. The moment the toy car enters the loop, the moment it hits the little bit of curvature, that brings it around a circle. The moment it hits this point here, I want you to draw the forces acting on the toy car now. Right, so the moment it enters in, right, so let's say it's somewhere around here like this, okay? I draw it a bit like that. Okay, the moment it enters in, right, can you tell me what happens to the N force and the mg force? Mg force remains constant, but then the N force will increase. Why must it increase? You need there must be a greater N force than the mg so that you can get a resultant force which will provide as the centripetal force, and this difference in the forces points where? Towards the center of the circle, which is around here like this. Okay, so the N force will increase. Now some of you may start asking me questions like this. How come you can suddenly increase a force like that? Right? There's a couple of analogies behind this. Okay, you can say that because of the curvature, the N force does increase. All right, but does it come at the cost? Like, oh, you can get a free force? Is it? No, right? It comes at the cost of like converting your GP into KE. Sorry, your KE into GP. You're going to lose some KE. You're going to convert it to GP, right? So the normal contact force is increased now like this. Okay? And okay, good. So that being said, can you tell me what is the equation used at the bottom here? So again, this is at the bottom, right? Right. This is NB, yeah. Right. What's the equation that you can write here? Right. NB minus mg equals to, I'm going to write mvb squared over r. Okay. NB minus mg equals to mvb squared over r. Ian, are you following? Yeah. Write this equation here. Okay. You understand that this VB stands for the V bottom, right? Right. This VB stands for the V bottom. That's the speed at the bottom. Okay. One more time. Will this car lose speed as it goes to the top? Yeah, it will lose speed, right? It will lose speed. It will lose speed because K is being converted to GP. It will lose speed, right? This car doesn't have an engine, right? It can't gain speed. It can't fight against gravity. It will lose speed, right, as it gets to the top. So once it's at the top, what's the equation for the guy at the top? What's the equation then? Or rather, what are the forces acting on this car? The N force is acting down. The N force is acting down. So the normal contact force at the top is actually acting downwards like this. And I'm going to put an NT as well, right? And then the mg is pointing down as well. So what's the equation for the car at the top then? NT plus mg equals to mvt squared over r. Are you okay on this? Can, right? Okay. Unfortunately, this is not that straightforward. Okay. As in, like, the question they like to ask for this kind of question is, what is the minimum speed to prevent the car from falling off? Understand this? They want you to find the minimum speed so that the car doesn't fall off. And I think, I don't know whether they've gone through this in school. They've gone through this in school with you? Minimum speed on top? You? You think so? Not yet, or don't know?
I don't think so.
Huh? So you never heard of this at all? Shit. Okay. Right. I'm just going to go through this, but because some of you have done it, I'm going to go through it a bit fast, okay? All right. Okay, so here's the thing. All right, listen up, huh? If this speed doesn't meet the minimum speed, what will happen to this car? It will lose contact. I want you to use the word lose contact. It will lose contact. I mean, yeah, you're right, it will fall, but it will lose contact. Okay? Because by saying that, right, you'll remember what I'm going to go through next. Right? It will lose contact. So if it meets the minimum speed, if it does have the minimum speed here, okay, if it does have the minimum speed, then what will happen to the car? The car will keep in contact. What's the fine line between losing contact and keeping in contact? having a contact force, right? Now, if your contact force is not 0, that means you are still in contact. If your contact force is 0, means you just lost contact, right? Understand this? Okay. So if you want to find the minimum speed, and this is a very popular question, they are always gonna ask you find the minimum speed. In fact, finding the minimum speed on top is not so hard. Later on, I'm gonna ask you, so therefore, what's the minimum speed of entry to make sure that he has enough minimum speed on top? This one will be a bit hard. Okay, the one at the bottom will be a bit hard, but I'll walk you through it, right? I'll give you all the equations here, and then we'll move on to the next part already. Right? Because some of you have done this in school before, so we're not going to spend too much time dwelling on this. So what's the objective again? What are you trying to find? You're trying to find the minimum speed at the top. See this? I put V min T. Right? V minimum at the top. Right? V min T. So to start this one off, I will tell you this, okay? To help you remember this, and I need you to remember this. Please remember, what is the worst case scenario? What's the worst case scenario to happen here? The car will lose contact, right? Drop off, it will lose contact, right? Okay. Worst case scenario, you lose contact. If you lose contact, what is the NT equals to? When you lose contact, what is the NT equals to? 0, right? That means you lose contact, which means that in the worst case scenario, you depend on the weight to provide for the centripetal force. You depend on mg. Let me just use a pink color, okay? mg equals to mv minimum t squared over r. Do you see that? I just wrote this down, okay? Right, so like I said, this one's a long journey. You have to follow me, yeah? Right? Ian, okay there? Can
Yeah.
Okay, thanks. Right, so mg equals to v minimum t. Again, where did the nt go to? Because worst case scenario, we assume that it just lost contact, or maybe we can consider it just haven't lost contact yet. All right, we make the contact force 0. So mg equals to v minimum t squared over r. And just very simply, v minimum t can be found, right, by just making it the subject. What do you get? You get root gr. You get root gr. So what's the significance of this? The significance is that no matter what's the mass of your toy car, right, the minimum speed is dependent on g and the radius of the circle. The bigger the circle, the bigger the minimum speed you need. But it doesn't matter what mass of the car you use. Okay? Right? But if you've seen I think there's a theme park, right, somewhere in the world where they show the Hot Wheels car, a life-size car going around in a circular track. It's a stunt driver lah. I don't know whether you've seen that before. Was it Warner Brothers or something like that? I don't know. It's one of those, like, they literally drive a car around a loop. So even if the loop is like, whatever size it is, right, that car must have that speed, that speed to go around the loop like this. Okay, it must have this minimum speed. Okay, no problems here. The tough one is this. The tough one is find the minimum speed at the bottom for the minimum speed at the top. Okay, the minimum speed at the bottom, V min B. Okay, right? The minimum speed at the bottom so that you can get the minimum speed at the top, right? In order to do this, you need to use energy. So you need to use energy. So what is the minimum KE at the top that you need? KE minimum at the top will be half m V minimum at the top squared. You all see that? Minimum KE at the top is half m. So if let's say part 1, right? If let's say part 1, they ask you to find something, right? Just take note that the minimum speed at the top is already found here. So it's just root of gr. Then this is like this is like part 2, right? This is like part 1, and then this is like part 2. Okay? Right? So if they ask you to find minimum speed at the top, you're done already. Don't need to go and do this next part. But if they want you to find the minimum speed at the bottom, then you have to do the continue on the next part. Okay. All right. Can you sub in the values here? What do you get? You get half mgr. Do you agree with this? Right. Half mgr. And therefore, the ke minimum at the bottom will be equals to, right? You see this term here? I'm writing this term here. Ke minimum at the bottom, right? Ke minimum at the bottom here is equals to Ke minimum at the top plus the GPE you need to cover the journey up. Okay, this part here, right? Please write this down. Ke minimum at the bottom equals to Ke minimum at the top plus GPE, and that's equals to half mgr plus GP is what? mgh, right? What's the h? 2r, so it's mg times 2r, and therefore the Ke minimum at the bottom happens to be 2.5 mgr. Okay, so the Ke minimum at the bottom will be 2.5 mgr. You'll see that there. Okay, yeah. And therefore, what is the V minimum at the bottom then? So V minimum at the bottom, right? This is half mv minimum at the bottom squared. So you take out the thing, then you will be left with root of 5gr. Agree? Ian, okay? You know why is it 5gr? Is half mv minimum at the bottom square, right? So you're just making v minimum bottom squared, the subject. So you times 2, it becomes 5, then you cancel the m, and then therefore you get root 5gr. Okay, part 2 is a bit more complex, but if you can understand what I've just done, right, that's it, right? That's all there is to it. The only issue is this, right? In rare years, like maybe once or twice in the last 6-7 years, okay, they have, and I don't know how, or they I don't know why, I don't know how they did this, or how it came to be approved. They have asked students to find the V minimum at the bottom in an MCQ question, right? Which means that they you know, the numbers will be nicely, because you're not allowed to use calculator in paper 1, right? But the numbers will be nice. It's just that it somehow seems to me that students are somehow expected to remember that minimum speed at the bottom is calculated as root 5gr. Otherwise, you have to do this whole thing, right? I don't know how long you're going to take for that one MCQ, right? So I have seen it once or twice before. I can go and show the picture, the question again, but yeah, it was quite surprising. And apparently, students need to know that like root 5gr is like the standard equation for minimum speed at the bottom. Okay, right. I am done with this. This one is one of the most difficult ones, right? If I'm done with it, I'm fine. Okay, but yeah, right. So if you get this kind of question, just take note. What are the most common questions from this? They would like to ask you what's the minimum speed here, what's the minimum speed there, and then that's the usual question, right? Can I do the one that's going over the bridge now? Right, the one that one of them was asking. Right, we'll do the one going over the bridge one. Okay, can. Okay, the one that's going over the bridge like this, right? The idea is this: as your car goes over a bridge, as your car goes over a bridge, the bridge is circular, which means that the car, as it goes around like that, right, is doing circular motion. It's a circular motion. And if it's doing a circular motion, what do you need? You need centripetal force, right? Circular motion needs centripetal force. So let's say the car is at the top of this bridge. Where should the centripetal force be pointing? Yeah, it should be pointing down, right? Because where's the circle? Where's the center of the circle? Center of the circle is here, right? The center of the circle is here. But once the car is on the bridge, right? Like on top of the bridge like this, what are the forces acting on the car? What are the forces acting on the car? The weight and the normal contact force, right? So, this one is the weight and this one is the normal contact force like that. Okay? Okay. Can you tell me this time round which one will be bigger? Yeah, weight has to be bigger, right? In order to go over the bridge, the weight must be bigger, right? Okay, the weight must be bigger than the end. So what will be the equation for the car going over the bridge? Good. Mg minus n equals to mv squared over r. Okay, and the r being this radius here, right? This is r. Beep 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 beep. Okay, hey, just want to point out to you, some students, right? I don't know why, but maybe it didn't hit them yet. This n, right, is not mg. Your job is to find what's the normal contact force sometimes, right? So don't assume that n is mg, then mg minus mg becomes zero, right? So don't do things like this, okay? So you should understand. Hey, your bridge not circular lah, dude. Your bridge like a rocket ship, no, dude.
Yeah.
You go up like that. Your cars go up like that. Okay, so draw this, okay. Now, are we okay with this so far? Can? Right, so this is your mg minus n equals mv squared over r. Mg minus n equals mv squared over r. The question now is this: what happens if you drive too fast? What happens if you drive very, very fast? You could fly off, right? Fair enough. If you drive very fast, you could fly off the bridge, right? Guess what, guys? If you fly off, what's the contact force? The contact force is 0, right? So you know what? I'm gonna ask you, what's the maximum safe speed that you should be traveling over this bridge? See, now you know the concept already. Now I'm just adding on another layer of questions, right? What's the maximum safe speed to drive over the bridge? So the idea is, if you are driving above this safe speed, means what? You fly off, right? Flying off is not safe lah, okay? Some people, that's not safe, man. That's okay, what? No, 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 okay? Don't fly off, right? Don't fly off, okay? But if you do, the normal contact force becomes 0, right? So we look for max safe speed, for example, max safe speed, right? If it's a maximum safe speed, then we will be looking for mg minus 0 equals to mv max squared over r. Now, even though I say this, right, I have seen some teachers twist this question before, okay? They twisted it in such a way that they say that, oh, this is a stunt race driver, and therefore they're trying to find what's the minimum speed required to fly off. It's the same thing, good, right? If I'm asking for the maximum safe speed, this is the equation. But if they twist the question and say that I want to find out what's the minimum speed to fly off because it's a stunt driver, right? Then it will be the same equation. It still loses contact, n is still equals to 0. Understand? Okay, good. Now if that's the case, then you can just simply write this: V max equals to dun, 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 same as just now, root GR. Okay, root GR. And okay. Now, Glendon does have a second part to this question, and the second part of his question is what happens when the car goes into a well, a circular well like that. Although it's quite unlikely, but okay. It's not him, it's the teacher's question, right? Like that. Okay? Right, so what happens if it goes into a well like this? Now, if it goes into a well, then the car, right, will be like that. What are the forces acting on the car? Mg and the N force pointing up. Does it have to be bigger than the Mg now? Why does it have to? Because you need a centripetal force pointing towards the center here, right? You need the resultant force to be pointing towards the center here like this. So what's the equation for the car at the bottom of the well? N minus mg equals to mv squared over r. Okay. Now here's the thing, okay? Right, I want you all to pay very close attention here. Huh? There is no need for safety here. There's no like safe amount of like there's no safe value of it. Okay, there's no safe speed or anything like that. It's not gonna fly off. If you're going into a well, right, the ng is bigger than the m, then the n is bigger than the mg at all times. It's not gonna fly off anywhere. Okay, so those kind of safety questions is usually at the top ones like this one, right? What's the minimum speed for this? What's the maximum speed for this? Right? This one, no, this one is whatever speed you want, right? The n force, right, will be bigger than the mg. That's it. And but maybe I will try to help you understand later on. Okay, so are we okay with this example now? Right? You can ask about safe speed here. You can't. There's not much need for safe speed over there. Are we okay? Can I move on? I can move on, huh? Okay, good. I'm gonna close this now. Right, I'm gonna close this now, and then I'm gonna ask you a fighter jet question now. Right. So now I want you to consider a fighter jet. Right. But you know what? I'm not gonna draw the fighter jet. I'm just gonna draw the chair with the pilot on it. Right, the pilot on here like this. Okay. Now I want you to understand that this fighter jet is gonna make a maneuver called the Cobra. Anyone watch the Maverick, the Cobra maneuver? You know what that was about? The guy fly, right? Then suddenly he just turns straight upwards like that. Right, that was a Cobra. Because in a dogfight, what happens is that the guy in front does this maneuver so that the guy behind flies forward, and then he comes back down behind him. Right, that's a tactical maneuver, but it's highly illegal even in today's uh, pilots. It's not safe because this maneuver gives the pilot very high g-force and may cause him to black out. And if he blacks out, that's it for him. He's done for it. He don't need the guy to turn back and kill him. The guy will just fall straight down to the ground. That's it. If he blacks out, okay. So the idea is that lah, right? So we're not gonna do something drastic as that. We're gonna just get this guy to go around in a circle, right, like this. Right? Let's just imagine that this plane is gonna start flying in a circle, and therefore, well, a question is asked. Our questions will be this: what are the forces acting on this on the pilot? What are the forces acting on the pilot in order to make this circle? Right? There's the mass of the guy, and what else is there? The normal contact force, right? The normal contact force. Now I'm just gonna be a bit like dramatic, huh? And draw this thing, oh, drama a bit, right? So draw a bit higher, okay, like this, huh? Okay, like this. I'm gonna come up with some numbers, and I don't know whether numbers make any sense, but I'm gonna tell you this. So the speed of this plane is at speed of sound is 330 meters per second. Let's say this guy is not traveling that fast lah, but maybe 200 meters per second. 200 meters per second. Okay, let's say he's traveling at 200 meters per second. Let's say the guy's weight is let's say he's a heavy guy, 800 newtons, right? Strangely enough, some fighter jet pilots are actually quite heavy. Yeah. Like you would think them to be lean and all that, right? There's actually a few of them. They're if you see the Singapore Air Force, right? Then some of them really very stocky, right? I don't know how it works though, but somehow they are built for it. Yeah. Really, I have no idea. Yeah. I like sometimes when they have those kind of air shows, right? Then they introduce the pilot, right? And you look like, serious? Really or not? Like, can man, this kind can become pilot, man. But apparently they are, and they're very high level pilots also. I don't know how it works, but okay. Okay, so there's a weight here, and let's say like I say again, I don't know the numbers here, so I'm just gonna assume that this is a 100-meter turn. Right? Let's say the radius of this turn is 100 meters. Okay, it's going at 200 meters per second. Right, it's gonna go into a circular motion where the radius is 100 meters. Right. The question now is I want to ask you to find n. What is the n force required? N required for this for the man to go around in a circular motion of radius 100 with a speed of 200 meters per second. Yeah, just that first. Let's no, let's get you to work on this, and then I'll explain a couple of things in a while. Right, we good. Finding? Anybody need help? Okay, now on the process, okay. You need the mass of the guy, which is not 80 kg, is somewhat less or more, right? Because you have to consider G is 9.1. So he's 81.55 kg. M is 81.55 kg, right? I just want to make sure everyone has the same numbers. 81.55 kg. Have you calculated N? How much is N? Was it 334 33420? Oh wow, okay. All right. I think I may have subjected this guy to too high to a very, very high amount. Way too high for me. Way too high. I think I caused this guy to die already. This guy's probably dead. I'm sorry. Okay. Why did I say that guy is probably dead? The N force required to perform such a maneuver, 200 meters per second. So I reckon that this is probably very fast. This is like maybe 2/3 the speed of sound. Okay, that means he's almost at Mach 1 already, right? 2/3 the speed of sound, 67% the speed of sound. And to do a turn of 100 meters, he needs this amount of N force. Okay. Now in topic 2, if you remember, what was the nickname that gave N forces? What's the nickname for normal contact force when it comes to, like, human beings? What's the nickname? Do you remember the nickname? No, no. I mean, it's a reaction force, but do you remember the nickname I gave this N force? Okay, it's quite important as we move on to gravitation. So I will tell you this intro. I remember. Okay, N force is also known as apparent weight. Right? Remember that apparent weight? I mentioned this before, right? So this N force is also known as apparent weight. Right? And do you remember what I said about apparent weight? What was apparent weight all about? Is the what? No. What did I say it was? It was a sensation, right? It was a feeling that you get, right? You say it's the idea that the feeling of the amount of force that you get, right? Okay, so obviously, guys, I tell you this, okay, my numbers are completely off, because the N required is 42 times, 41.8 times his 41.8 times his mg, okay, right? Most people will pass out at 9 Gs. So if it's 41.8 mg, this guy is probably dead, right? Yeah. Right, like fighter jet pilots, right? At their best training, they can withstand 9 Gs, but if it's 41.8 Gs, that's off. All right. So the trick here is to understand that this is what it means. It means 48.1 Gs. Right? Do you remember, like, if you watch documentaries or you watch shows, right? They say things like this, right? Oh, the guy will pass out at 9 Gs. The guy will pass out at 7 Gs. Right? What does it mean? What does G mean? Gravity. So does it mean that the guy will pass out when the G like multiplied by 7? How does the Earth's gravity go up by 7? It doesn't, right? It's not the Earth's gravity that is multiplied by 7. What is it? It's the apparent weight that he experiences, right? So the safe amount, all right, or rather the limit of humans is about apparent weight is 9 times that of the weight of the guy. Right? So if we go up to like 41.8 G, this is way too much. Right? This is obviously too much. This is not a possible maneuver. Maybe you have to increase the radius. Maybe my radius is a bit too small. Maybe you have to increase the radius to like 500 or maybe 1 km. Right? Which is fine because for planes, right, when you fly at that kind of speed, right, 1 km is covered in a short amount of time. Right? So maybe this circle is too small. It's a very tight circle. So yeah. Right, this guy's gonna die. All right. All right, there you go. So this will be for another scenario for circular motion, right? Vertical circle. Okay. Not realistic, but there you go. Right, there you go. And I think I've covered almost everything except the rigid rod, right? Which is what I'm gonna do now. Okay. Now the reason why I want to do the rigid rod one is because at the last part, because it doesn't really come out in recent years, right? But since we have SOTA on board, so we have to consider this. Okay, they make it a point. I don't know why. Have you heard of them talking about it in class? Yeah, a rigid rod. Really? Yeah. See, they make it a very big point. I can guarantee you that the rest of them they don't bother. Because it comes out as a one MCQ question like one time, like that one time, and then suddenly they make a big fuss about it. Like what? Okay, rigid rod. Right, last thing for today, rigid rod, and I can go on to gravitation next week already, right? Oh, I say I wanted to go on gravitation today, right? I can't make it by then. Right, rigid rod. Right, I want you to imagine you are Thor and you are swinging the hammer around in a circle. Okay, so imagine you're Thor and you're swinging the hammer around, right, in a circle. Right. So this is not a string. This is not a string. This is a rigid rod. Okay. Okay, I want you to know one thing, okay? For rigid rods, right, you can maintain the speed. You can maintain the speed to be constant the whole time. That means you can control the speed because you can't do this for a string. A string doesn't have the kind of force that enables you to like keep the speed constant. Or if it's a string, right, this object will lose speed as it goes up for sure. But because it's a rigid rod, I can control it like this. You see this pair of chopsticks here? Right? I can control it like that. You understand? I can control it like this. Right? I can control the speed. So the speed can be constant. For a pendulum on a string, it can never be constant, but a rigid rod can be constant. Are we okay on this? Can Okay. Right. And then for rigid rods, what's the most popular positions to ask? On the side. They love to ask on the sides one. Right. So For this object to go around in a circle, there must be a tension force still, and it must be pointing towards the center. Do you understand this? Right? There must be a tension force still, and it must be pointing around the center. Okay? But one other force that this rod can give the mass, right? One other force that the rod can give the mass is this force here. Right? I'm just going to call it F like that. Right? This force is like a pushing force. It kind of helps to lift this object up. But what should it try to balance? It should try to balance the weight, right? Right? The lifting force must balance the weight. You understand this? Ian, okay there? Can this force, right? Okay. So this T and this F are both from the rod acting on the mass, right? This is the lifting force, and this is the tension that gives you the centripetal force. Correct? Okay. I want to combine both T and F. If I combine both T and F, what will happen? I will get a force that looks like this. The force by the rod, right, acts like that. So some of you may be asking me, but it doesn't point in the center, leh. How? But that's the whole idea is that if you resolve it, you will have a component that points towards the center, because the vertical component is meant to balance the weight, right? If it's more than the weight, then the object will accelerate. If it's less than the weight, then the object will decelerate. So this upwards force must be equals to the weight. Are you okay with this? You understand this so far? All right. Now, of course, when you get to the top of the object, when you get to the top position, right? Once the object is at the top here like this, right? When the object is at the top here like this, then the force on the rod is just pointing down, right? Because there's nothing else for it to do, right? So it just point downwards like this. So the force on the rod will keep changing. It will go like that. You see, this is the force on the rod, right? Like this, right? As you go higher and higher and higher, the force will rotate until it becomes vertical like that, right? So it goes like this, Ian, like that. You see, right? So as you go up, as the object goes up, right, the force by the rod will rotate like this until it becomes vertical. Okay, right? So that's the yeah, that's the thing there. But then the question is, on its way down. So if let's say it's going up like this, right? And how about on the other side, on its way down? What's the direction of forces acting on the object on the way down? So as the object falls down, right, you would expect the speed to increase, right? Wouldn't you expect the speed to increase as it goes downwards like this, right? As the object goes downwards like this is like the Singapore Flyer, actually, right? As it goes down, it will increase, right? Can you imagine if that happens in Singapore Flyer? Oh my god. Right, it becomes a nightmare, man. It becomes like a roller coaster already. Of that size, that's a huge roller coaster there. So you need to maintain the speed because you still need to attract your visitors, right? Oh no, incidentally, the Singapore Flyer is not functioning now, right? Right? Do you all realize that it's closed down for a long time because company that ran it went bankrupt? Yeah. But do you know why the lights are still on? For sure. Do you really want to have a national icon not being lit up? Right? You still have to put it on for sure. All these kind of things, right, that they have to do, right? So strange. And they don't dare to tear it down also because like it's supposed to be an icon, right? I'm sad. Anyway. So in order to prevent the object from gaining speed as it falls down, the rod must apply an upwards force again. So again, you're gonna get this upwards force and you're gonna get this centripetal force, right? The tension that provides for the centripetal force, and therefore the force by the rod, even as it goes down, the force is also still pointing at the upwards angle like that. Right? While mg is still pointing downwards like this. You get it? Right? And this is how the rigid rod system can maintain the speed. This is how it maintains the speed. What's the objective? The objective here is to maintain the speed. Right? The objective here, the force, right? F rod acts in these ways to maintain v of circular motion, right? Then the question is why, right? Why? Because you want to maintain the speed, right? It's a matter of choice, right? So the idea is that if you want to maintain the speed, then the force by the rod acting on the mass must act like that, right? If you since you want to, okay, all right. And I'm gonna tell you this: I'm pretty much done with circular motion, like you know, the horizontal circle, vertical circle. I went through as many scenarios as I can. I went through this weird one. I'm not surprised if you have more or you have different kind of scenarios, but you follow the basics I have taught you so far. Okay. So for homework, okay, not much. Homework is what? If I give you any homework, right, it'll be like the same question. Yeah. So it'll be the same questions I have. Oh my gosh, I wanted to screenshot that. Hang on, just to remind you. So for this one, usually no calculations. Usually, don't know whether they've given you any calculation questions, but it kind of like I think the question, the IB question itself was this also. They asked the students, where's the direction of force? Which diagram is correct? So you have to make sure that you understand that you're looking at a rigid rod where the speed is constant, and therefore since the speed is constant, the force must be acting like this. Okay, hang on. Okay, so homework is this, guys. Listen up, 4, 5, 9, 10. Wait, homework 4, 5, 9, 10. 4, 5, 9, 10. 11, 13. Sorry, 4, 5, 9, 10, 11, 12, 13. 12 is just a variable, it's just a algebra question, right? But it's one of the usual ones. 4, 5, 9, 10, 11, 12, 13. Yeah. Okay, then, all right, that's the homework. Legit get it done. Also at the same time, you I don't know whether your school is going through all the dynamics questions, the topic 2 ones, right? But I must tell you this, okay? Don't let it snowball, right? Your especially your school will go through very fast. I think your school also will start to go through very fast. Yours is similar pace, maybe 1 or 2 topics off, so it's not so fast, but it will start to snowball, the amount of work. So once you clear the work already, right? Once you clear the work already, then you know you're rest assured that you should know this well enough for the exams. Okay. Next question, I want to check with you. You all confirm don't have a July exam, right? Confirm July don't have mid-year exam, right? Because yeah, they I think they don't want to stress you all too much or something like that. Okay. So just make sure that you all do all the questions that I give, or do your school questions. Okay, bye guys. Treasure. Give me the treasure. Yeah.